doesn't obey usual Helfand this Hohenberg picture. But what is the difference between the dependencies, temperature dependencies of the upper critical field for samples with spin density wave and without spin density wave? Did you observe some differences?
Okay, thank you very much for the question, but H2, in superconductive samples there is no spin density wave, so you cannot compare the sample. If you have spin density wave, that means that you have inhomogeneous in your sample. Usually, if you appropriate doping, spin density wave is gone. Nothing. Only this is a phosphorus doped sample, which we have very underdoped sample, you have some kind of coexistence. But in fully oxygenated band, there is no any spin density wave in this material. Only you see some kind of curvature in resistivity, which maybe remind that still there is some kind of fluctuation and so on and so on. But HC2 is mostly determined by, I think, the structural parameter, and from this structural parameter and the sound opinion. And this behavior is not very well understood. We make a scaling to understand what kind of pinning in this material, and we found that there are only one kind of pinning. But this work we just continue and just going on.
It's practically impossible to extract up a critical field from resistive measurements, because all this region of broadening corresponds to flux flow because of strong fluctuation. And in some other elements, it seems to be exactly the same. So I think that you strongly underestimate HC2 extracting this curve.
Yeah, so this is why we use two techniques, magnetic and the transfer.
Both have the same problem, broad.
Yeah, but this
is fluctuations. So
what you can do in the process. But we also measure transfer directly. We make a bridge.
Doesn't matter. You measure transfer correctly, don't doubt. It's impossible to extract HC2 from it. Okay, there's last question.
About iron halogenides, do they fit into the same scheme or maybe this? Separate?
Yeah, thank you, Dr. What I showed this in principle, this is just a general tendency. Now, if you look for each family, they have their own figures, their own feature. So this is what I preserve. This is the general for iron arsenide. Halogenides is a little bit different. But halogenides is completely different system. So I will not say. I would just call like a general behavior. If you want to say what the highest TC you can do, what kind of parameter you need. In general, this is correct, but in detail, it's not.
Very good crystals of 1,1.
Thank you much. Your study, I didn't mention your work.
However, also in these perfect crystals, you have 50% of fluorine substituted with oxygen, and this is make a big disorder in the system. Do you know anything about the distribution of these dopants?
Yeah, this is what we want to know, because probably this also can work like a pinning. Who knows? So just itself to check the fluorine is very complicated. What we did, we just make a BDX analysis, wide dispersion X-ray analysis. We polish the polycrystalline materials, and we measure the grades, and we see the distribution of the fluorine in different grades. And this distribution, of course, is homogeneous, but not so pure. So there are inhomogeneity, but it's some kind of way, but I cannot tell you the exact region. You're absolutely right.